Let us now discuss yet another connection of the BJTs. This is called the Darlington connection. So you see that each BJT is having a unique parameter called the beta or HFE, which relates the collector current and the base current. So beta is nothing but collector current divided by the base current, ratio of collector current to base current. So higher the beta, smaller will be the base current for a given collector current. What it implies is that for a given collector current, one can use the base drive of the BJT with lower sourcing capability circuits. And this is a major advantage. So how does one increase the value of beta? Of course, one can go and purchase a BJT looking into the data sheet, one which has a high value. A single transistor BJT having beta value very high, much greater than 100 is very difficult, and that is where Darlington connection comes into the picture. So take two transistors and connect it in this fashion. You have the collector, base, emitter. The emitter of first transistor is connected to the base of the next following transistor. The collectors of both are connected together in this fashion, and the emitter of the second transistor will become the emitter of the combination. Base of the first transistor will become the base of the combination. Now you need to put two resistors in this fashion between base emitter junction of each of the transistor. The reason that you need to put this is that you need to have a path for the stored charges in the base to recombine. Remember, recall that in the dynamic characteristic discussion, we saw that for the BJT to turn off, you need to remove the base stored charges, and for that there is a negative current, base current that needs to flow. So now this is the path for this first transistor, and for the second transistor this is the path. So there is these two resistors that are required. So this combination is called the Darlington connection, collector, base, emitter of the combination. Now if beta 1 is the beta of the outside transistor and beta 2 is the beta of the inside transistor, the overall beta is approximately equal to beta 1 into beta 2. One can easily see why this is so. So consider a collector current IC flowing in this fashion. So this is the collector current, the base current and the collector current are related by beta 1. So the base current for this first transistor will be IC by beta 1. Now IC by beta 1 is the emitter current of the second transistor, which is approximately equal to the collector current of the second transistor. It has a beta of beta 2, and the base current of the second transistor will be IC by beta 1, which is flowing as the collector current approximately divided by beta 2, so which would be IC by beta 1 beta 2. So therefore the base current of the Darlington combination is beta 1 beta 2 times lower than IC. So that is why the overall beta comes out to be around beta 1 beta 2 approximately. So this whole combination like this is available as a single IC pack. For example, TIP 122 is a Darlington pair. You also get it in the complementary. TIP 127 is a PNP version. TIP 132 is a NPN version. They have pretty high betas, HFE of even 1000 approximately. We will have a look at the data sheet later. Or you could also build the Darlington pairs discretely. You can use discrete transistors and resistors and build the Darlington pair discretely to achieve your own customized beta. This is probably something that you can achieve around beta of 1000 or so. So Darlington connection is a pretty important connection people use for improving the current gain, collector to base current gain.